In a nuclear war, the first targets are not cities. They are eyes and brains. Early warning radars, satellite control rooms, command centers. If those are destroyed in the first minutes, a country can lose the ability to understand what is happening and to respond. For the United States in the 1960s, that vulnerability was not theoretical. Missiles in Soviet silos could cross the Arctic and reach American territory in about 30 minutes. A single megaton-class warhead detonated over a major command center could erase it in a flash. The question was brutal. How do you keep control of your defenses when the surface of your country might be burning? The answer was to move the brain of the air and missile defense system inside a mountain and make sure it could survive a direct nuclear hit. The mountain they chose sits just southwest of Colorado Springs in Colorado. Cheyenne Mountain is a block of hard granite more than 1 billion years old. That granite is dense and relatively free of major faults. Earthquakes in the region are rare and mild. The site is far from coastlines and away from likely naval missile launch areas, but close to existing Air Force installations and communications links. In 1961, construction began on one of the most ambitious underground structures ever attempted. The goal was not a simple bunker. It was a self-contained underground complex that could host hundreds of people, process data from radars and satellites, and continue operating after a nearby nuclear explosion that would level everything on the surface. Work started with the most basic but hardest step. Remove enough rock to create space. Crews drove tunneling machines and drilling rigs into the mountain. They drilled patterns of holes into the granite, packed them with explosives, and fired them in controlled sequences. Each blast fractured a small part of the rock face. Heavy equipment moved broken stone out of the tunnels and down the mountain roads day after day. Over several years, workers removed approximately 693,000 tons of granite from inside Cheyenne Mountain. That is about the same as removing the weight of several large aircraft carriers, but all of it in the form of drilled and blasted rock carried out through tunnels. The tunnels they created are not narrow mine shafts. The main galleries are roughly 14 meters wide and nearly 20 meters high, large enough to drive trucks through and tall enough to hold multi-story buildings inside. Instead of carving rooms directly into the rock, engineers decided to build a cluster of separate steel-framed buildings within these caverns. There are 15 such buildings, each 3 stories tall. They look like a small industrial park that just happens to sit inside a mountain. The choice to build separate buildings allowed engineers to control interior layouts, support heavy equipment, and replace or upgrade structures without touching the granite around them. The most distinctive feature of those buildings is how they are supported. They do not rest directly on the granite floor. Each building sits on a set of large steel coil springs mounted on concrete pedestals. There are more than 1,300 springs in total. Each spring weighs hundreds of kilograms and can carry loads measured in tens of tons. The idea is simple but powerful. A nuclear explosion generates an intense shock wave that travels through rock like an earthquake. If the buildings were fixed to the rock, that shock would be transmitted directly into their frames. By placing them on springs, engineers created mechanical filters. When the rock shakes, the springs compress and extend. The buildings move, but more slowly and gently than the rock itself. Calculations and tests showed that this system would keep structural loads within safe limits, even under severe shock. Protecting the entrance required a different kind of engineering. Cheyenne Mountain has a main access tunnel that slopes gently down into the complex. At the outer end of that tunnel, and again further inside, sit massive blast doors. Each door weighs about 25 tons. They are made from thick steel plates backed by concrete. When closed, the doors lock into steel frames embedded in the rock. The seal is designed to withstand the overpressure from a nearby multi-megaton nuclear detonation. In simple terms, if a nuclear weapon exploded close enough to flatten surface buildings for kilometers around, the shock and pressure at the doors would not be enough to tear them from their frames. Hydraulic systems can open and close these doors in under a minute. If power is lost, they can still be moved manually, though slowly, using mechanical gear systems. When the doors are closed, the complex can be pressurized and isolated. Power is a key vulnerability in any hardened facility. Cheyenne Mountain cannot depend solely on the civilian grid. Inside the complex, engineers installed multiple large diesel generators. Each generator is capable of producing significant electrical power, enough to run computers, lighting, ventilation, pumps, and communication systems. Fuel is stored in underground tanks with capacity for extended operation. The layout separates generators in different rooms and supports independent fuel lines so that a fire or mechanical failure in one set does not shut down the others. The electrical network inside the mountain is designed with redundancy and protection against sudden voltage spikes. Many components are located deep within the granite, using the rock itself as a shield against electromagnetic pulse, the intense burst of energy produced by a nuclear explosion that can damage unprotected electronics over vast areas. Water supply is handled in a similar way. Wells and storage reservoirs inside the mountain provide the complex with water independent of surface systems. Plumbing distributes water to restrooms, kitchens, medical rooms, and cooling systems. Wastewater treatment facilities inside the complex handle sewage, reducing the need to rely on external infrastructure that might be damaged in a war. Ventilation systems pull in outside air through shafts, but can also close off and recirculate air inside the complex. Large filters remove dust, radioactive particles, and chemical contaminants. The ventilation network is designed to maintain slight overpressure inside critical areas, so that if there is any leak, air flows outward rather than inward. This reduces the risk of contaminated air seeping in through small openings or damaged seals. The complex was meant to support a significant staff for extended periods. Designers allocated space for dormitories, dining facilities, medical bays, and even a small chapel and recreational areas. Sleeping quarters use bunk beds arranged in rotations, so that beds are occupied around the clock by different shifts. Food storage includes dry goods, canned goods, and refrigerated supplies. Kitchens are equipped to feed hundreds of people 3 times a day. The medical area can handle routine health needs and emergency trauma. Everything is laid out with redundancy. More than one kitchen, more than one medical room, more than one set of restrooms. The assumption is that damage or fire might take out parts of the facility, but operations must continue elsewhere inside. Cheyenne Mountain's purpose is early warning and command. From the start, it was built to house the North American Aerospace Defense Command, or NORAD. NORAD monitors the skies over North America for aircraft, missiles, and other objects. To do this, it uses a network of radars on the ground, sensors on aircraft, and satellites in orbit. During the Cold War, radar stations stretched across the northern United States and Canada, scanning for Soviet bombers and intercontinental ballistic missiles. Ballistic missile warning radars in places like Greenland and Alaska watched for launches over the Arctic. Satellites in high orbit looked for the infrared signatures of missile engines igniting anywhere on the planet. All of that data converged at Cheyenne Mountain. Inside the mountain, large operations rooms are filled with consoles and screens. In the early decades, these were massive mainframe computers, analog displays, and wall-sized maps. Operators tracked every contact, from commercial airliners to potential missile launches. When sensors detected something unusual, data flowed into the mountain within seconds. Software and human analysts evaluated whether a blip on a radar screen represented a real threat or a glitch. If the system judged that an enemy missile launch was underway, protocols required rapid confirmation. Trajectories would be computed to determine impact points and timelines. This information would be passed up to political and military leadership to make decisions about retaliatory strikes. The entire process from detection to decision could unfold in 15 to 20 minutes. There were incidents that showed how high the stakes were. In November 1979, a training tape simulating a large Soviet missile attack was accidentally loaded into a live system. Displays used by NORAD and other command centers began showing hundreds of incoming missiles. For several tense minutes, personnel at Cheyenne Mountain and other sites worked to verify whether the attack was real. Independent radar and satellite data did not confirm the launches, and the alert was canceled before any retaliation occurred. In June 1980, a malfunctioning computer chip caused systems at Cheyenne Mountain to report a false missile attack again, indicating that dozens of missiles had been launched from the Soviet Union. Once more, cross-checks with other sensors showed no actual launches, and no missiles were fired in response. These episodes demonstrated both the importance of having multiple independent data sources and the nerve required from officers inside the mountain, who knew that a wrong decision could start a nuclear war. During construction and testing, there were also reminders that building a fortress inside a mountain is not a risk-free job. Drilling and blasting granite is dangerous work. Rock falls, misfires, and equipment accidents are constant threats in that environment. Crews worked in shifts, often in dusty, noisy conditions with heavy machinery inches away. Safety standards were applied, but like any large construction project in the 1960s, there were injuries and near misses. Each blast had to be calculated so that the shock did not crack the surrounding rock in unintended ways. Engineers constantly monitored for signs of structural instability and reinforced weak zones with rock bolts and steel mesh. The goal was to create a stable hollow inside the mountain without compromising the strength of the rock shell that protected it. Cheyenne Mountain also had to be defended in everyday terms. The entrance area has fences, gates, and guard posts. Vehicles approaching the tunnel are checked thoroughly. Inside, access to sensitive zones is controlled by identification checks and security doors. Communications lines connecting the complex to the outside world are diversified. Underground cables run along different routes. Radio and satellite links provide alternative paths. Although some details are classified, the structure of redundancy is clear. Losing one line cannot sever the complex from the rest of the defense network. The end of the Cold War in 1991 changed the political environment, but not the basic physics of nuclear weapons. The main threat of a massive Soviet first strike receded as the Soviet Union dissolved. Budgets shrank, and new above-ground facilities with modern computer systems were built nearby at Peterson Air Force Base. In 2006, many of the day-to-day NORAD operations moved from Cheyenne Mountain to those surface buildings. However, the mountain complex was kept in a state of readiness as a backup and as a home for particularly sensitive systems. In the 21st century, concerns about high-altitude nuclear detonations and advanced electromagnetic pulse weapons brought renewed attention to Cheyenne Mountain. Hardened as it already was, the complex offered natural shielding thanks to hundreds of meters of rock overhead. In 2015, officials announced that certain space and missile warning functions would move back into the mountain, specifically to benefit from that shielding. Modern military operations depend heavily on electronics and data links. An electromagnetic pulse that disables satellites, radars, and computers across a continent would be devastating. Placing critical command systems deep underground, in a location intentionally designed to resist both physical blast and electromagnetic effects, adds a layer of resilience. From the perspective of engineering and architecture, Cheyenne Mountain is a clear example of what might be called survival infrastructure. Instead of being optimized for cost efficiency or aesthetic appeal, the complex is optimized for continued function under extreme stress. Its defining metrics are not comfort or beauty, but shock resistance, redundancy, and autonomy. It is designed to keep working when much of the surrounding world does not. Its existence is an admission that deterrence might fail, and that someone must still be able to think clearly and issue commands if that day comes. For the people who work there, daily life is less dramatic than the facility's purpose suggests. Technicians and officers arrive, pass through security, and descend into the tunnels. They sit at consoles, monitor radar feeds, satellite tracks, and communication channels, and respond to routine anomalies. Most days, nothing resembling the end of the world happens. But training includes scenarios in which alarms sound, blast doors close, and the complex shifts to fully sealed mode. Air intakes switch to filtered recirculation. Generators spin up to carry the full load. Personnel move to predetermined stations. The mountain becomes a closed system, running on its own. Cheyenne Mountain is not unique in concept. Other nations operate hardened command centers under mountains or deep underground. There are similar facilities in Russia, Europe, and Asia. Yet Cheyenne Mountain remains one of the most fully documented and most technically elaborate examples. Its spring-mounted buildings, massive blast doors, and multi-layer life support systems represent a specific philosophy of survival. Do not trust the surface. Assume that everything above a certain depth can be destroyed. Put what matters below that line, and design it so that it can run by itself. In raw numbers, the complex speaks for itself. 693,000 tons of granite removed to make space. 15 three-story buildings on more than 1,300 steel springs. 25-ton blast doors guarding the main tunnel. Hundreds of meters of rock overhead, enough to shield against blast pressures and electromagnetic pulses from multi-megaton nuclear detonations. Generators, fuel tanks, wells, filters, and food stores laid out to support hundreds of people for as long as needed. Billions of dollars in today's money invested over decades. Cheyenne Mountain shows what it looks like when a society spends real resources on a single, narrow goal. Keep the national command structure alive and thinking in the worst possible hour. It does not solve the problem of nuclear weapons. It does not protect cities or civilians. It does not prevent war. It only ensures that if satellites detect missile launches and radars confirm trajectories, there will still be a protected room somewhere with working screens, working phones, and people who can make decisions. It is architecture built not for comfort or profit, but for the survival of a decision-making process under conditions where almost everything else fails.